Hi guys, this is Dr. Gonzalez here, and today's lecture video is going to be about data and variability. This is an important concept in our descriptive statistics unit, and it's building off what we have discussed in frequencies and in central tendencies. So if you haven't watched those two videos, I recommend that you go back and do so. So what is variability? Variability is going to be how our scores in our distribution differ from one another and how they differ from the center. So in other words, we're looking at the differences between the different scores and how spread out or clustered they are. And you can see underneath here I've given you two example distributions. The first one is adult height in inches, and you can see that it is a much more narrow distribution. The scores, that is, are much more clustered around the measure of central tendency, the mean. And in the second distribution, we're looking at adult weight, and you can see there's a lot more variability in this particular distribution because the width of our distribution is much larger, and the distribution itself looks like it's stretched out from both ends. So you might be thinking, why do I need to know about variability? We just discussed central tendency, and you said that was a super important part of a lot of the inferential statistics that we'll be dealing with later. And that's true, right? But central tendency is not the only thing we need to know about our data, because it's quite possible that we have two different data sets and they have the same mean mathematically, but as a distribution, they look very different. And central tendency is going to focus on that center of the distribution and leave out the important part of the spread. So both of these things are vital components to doing our statistics. So consider these two distributions that I've put here in an image for you. Both of these distributions have the same mean right here in the middle. However, you can see that distribution A is much more spread out than distribution B. So if I were only to focus on the central tendency of these two distributions, I would miss a lot of the nuances about how the data actually look. So that's why it's important to examine both of these particular aspects of data. What does variability do for us? Well, variability describes our distribution in a more complete way. And it does so by indicating how well that mean actually represents that data. So it works in conjunction with the mean because it's telling you the distance in average a particular score is away from that mean. And so it is going to play an extremely important part in inferential statistics. And that should say play and not plays. So when we interpret variability, what is it telling us? Well, when you get a low measure of variability, it's telling you as a researcher that your scores are similar to one another. And they're going to be clustered around the mean. So they're not going to deviate that much. A higher variability means your scores are more widely dispersed and spread out, and that means that your mean is not as good of a representation of the distribution itself. So we need to take that in consideration with our statistics. So let's talk about variance and standard deviation and how they play off of one another, and also how you are going to calculate them. So variability is measured using variance and standard deviation. Variance is your average of the squared deviations from the mean, and your standard deviation is the square root of that variance. And below here you can see that I have included for you the various formula that you would use for variance and for standard deviation if you're dealing with a population versus a sample. And sure, these look very complicated, and they can get a little tricky if you are calculating all of these by hand, but luckily we have great statistical software that can do this for us, but it's still important to understand the concepts behind the actual calculation. So we're going to deal primarily here with our population variance formula and our population standard deviation when we're trying to understand what's actually going on mathematically. So variance and standard deviation use the population mean, or mu, and it's going to divide by n, which is the number of scores in the distribution. And that particular formula gives us a true representation of the variability of the entire population. Remember, when we're dealing with a population, if I were to actually talk about variance and standard deviation for a population, I'm referring to everyone in that population, not a sample. We'll talk about how that's different a little bit later on. But the standard deviation is going to represent one score's average distance away from the mean in the original units that we were talking about. So if we're talking about feet, we're talking about hours, it's represented in those units. So if your sigma is small, your scores are going to be tightly clustered. If your sigma is large, then your scores are more spread out. Here are the two formula for our sample variance and sample standard deviation. And you'll notice there's a difference here. Instead of n, I'm dealing with n minus 1. You're probably going, why? Well, n minus 1 is going to start to introduce the concept of degrees of freedom, which is something that has to be reported with our statistics. So we're going to represent that in our reporting as saying degrees of freedom is equal to n minus 1. So if I have 200 people in my data set, I'm going to subtract 1 from it, and my degrees of freedom are 99. And that is because one value is constrained by the mean. So only n minus 1 scores are free to vary. One of those is the mean. That's what that is telling us. So it's correcting bias in estimating that population variance, and it's giving us an unbiased estimate. And that means when we're talking about sample variance, we're talking about it in a context of being unbiased as a statistic. This is because your sample variability is going to tend to underestimate your population variability. Remember, we're dealing with a sample, and that sample does not include all of the members of the population. So what it's doing is it's artificially minimizing the deviations. So our solution to that is to correct for it by using n minus 1. What that does is it slightly inflates our variance, and it compensates for any underestimation that might be included in that, thus producing an unbiased estimate of that population's variance. And I hate this when it happens here. I lose my cursor. So the alternative calculation in the simplified formula uses this particular formula down here. It avoids computing each deviation individually, and we're going to go into this a little bit more in detail later on. So let's talk about what variability and distribution shape look like here. So we talked about having a larger spread that would indicate having a larger variance or standard deviation. So that's what we're dealing with right here. I have this distribution, and it's much more spread out, and we can assume that these distributions have the same mean, right? And that's why we were talking about how central tendency loses part of the nuances if we only depended on that when we were talking about it. We compare that to a smaller standard deviation right here. I have more clustering around that mean, and that results in a smaller variance and a smaller standard deviation. So you need to remember that variance and standard deviation are going to be sensitive to extreme scores, just like the mean was. But this is important because that outlier there is going to increase our variability significantly. So we're talking about the distance from the mean for a particular score. So if the mean is in the middle and an extreme outlier is on the end, obviously that individual score's distance from the mean is much greater than a score that would be much closer to the mean. So we're going to interpret standard deviation as the typical distance away from the mean. So variability is going to depend on that mean, and the mean is going to provide you a reference point when you're talking about those deviations. So variance and standard deviation are fundamental when you're computing a z-score, when you're examining a normal distribution, when you're dealing with hypothesis testing, and then in other more complicated statistics, inferential statistics such as ANOVA and regression. So here is a very simple activity that you could do on your own by hand. You have a psychology professor teaching a graduate stats class, and she recorded the number of hours each student studied for an exam, and she got the data that is listed here. The data are 6, 8, 5, 9, 7, 6, 10, and 9. So that is a distribution of hours studied. So you can easily calculate the mean, right? We all know how to do that. Once you have the mean, you could list out all of your scores, and you could figure out how the deviation from the mean is for each score. So that's x minus m. So if I have 6, you would say 6 minus m. And you would see that you might get a negative number, right? So we're going to correct for that by squaring our deviations right here, x minus m squared. Then we find the sum of those squared deviations and plug it into our formula to get our sample variance, and then we take the square root of that to get our standard deviation. So you could easily open up Excel and you could tell it to calculate the mean of the data set. You could list x there and get our mean of 7.5. Then you can plug it in and tell it in the formula bar to take and compute for this cell right here and say 6 minus the mean. And then you could tell it in the next one to square whatever is in this cell. So that is where we compute our deviation from the mean. That's x minus m right here. And then our squared deviations are right there. And next you're going to find the sum of those squared deviations. So you just add up everything in that column right there, and we get 18. And then we use our formula right here to get on our numerator 22 and our n minus 1. There were 8 people in this sample, so 8 minus 1 gives us 7 for our degrees of freedom. And we would divide and we would get a s squared of 3.14. And if I took the square root of that, I would get 1.77. So that is a very quick and dirty explanation of standard deviation and variance. I'm going to include in your class a more detailed video that will show you how to do this with a data set in Jamovi, and that will be posted pretty soon. But I hope you have learned something by watching these 3 videos together: the frequency, standard deviation, and variance. And these are going to give you your basic introduction to what we are going to need to know before we move into more complicated topics in both Psychology 4370 and 4371. Thank you, and I hope you enjoyed the video.